In this video, we're going to work through a number of least squares problems. Note that we don't want to reinvent the wheel each time, so while the other video was important to know why this process does work, this is the video you want to pay the closest attention to in order to know what the process is to solve these kind of problems. Now, since I made these problems using some basically random numbers, we shouldn't expect our solution to come out very nice. We'll be getting some fractions here, but this is pretty typical of these kind of situations. So here, I have this system here. It has two variables, but three equations. We shouldn't expect to expect to have a solution at all, really. In fact, technically, this system does not have a solution. But we are going to find the closest solution. We want a least squares solution to this overdetermined system. So where do we start? Well, we're just going to start by naming our matrices. We'll start with the matrix A. This is our coefficient matrix. So we have 4, 6, 1, negative 5, and negative 3, 2. We have our matrix B. This is our constants, our 5, 7, and 1. We kind of don't even have to look back at our system anymore, though note I'm just going to use x and y rather than x1 and x2 just to keep it simple. We'll go ahead and take the transpose of A. I'll just go ahead and write it over here. So our first row is 4, 1, negative 3. Our second row is 6, negative 5, 2. And now we are going to multiply both A and B by A transpose. Remember, we're multiplying them both on the left. So what is A transpose A? If we multiply these together, so we multiply the, well, kind of maybe it's a little tricky because they're on the opposite sides of the screen, but we're taking rows of A transpose times columns of A. So the 4, 1, negative 3 is going to be multiplied to 4, 1, negative 3. We're actually going to be adding up a bunch of squares. That might be where the term least squares comes from. So we have 16 plus 1 plus 9, and we are going to get 26. Then we do 4 times 1, or 4, 1, and negative 3 times 6, negative 5, 2. This one's not squares, but that's okay. So we have 24 minus 5 minus 6. We're going to get a 13. In fact, if we look at the other one, over the one down in this corner, we're going to take now this row, 6, negative 5, 2, and we're going to multiply it by 4, 1, negative 3. In fact, we're going to get the same numbers multiplied together and added up. We're going to get the same 13 that we got last time. And then finally, we're going to take the row 6, negative 5, 2 times 6, negative 5, 2. Again, we get a bunch of squares. When we multiply those together and add them all up, we get 65. That's our A transpose A. And just to kind of note here, what I said about those 13s being the same, that's always going to be true. We call this symmetric. That's our term for it. Basically, that if we reflect over this main diagonal, we always get the same thing on either sides. And this actually comes in from the fact that if we take the transpose of A transpose A, remember the transpose will swap the order of the product, and then we have A transpose times A transpose transpose, but A transpose transpose is A. Essentially, taking the transpose of this product A transpose A doesn't change anything. We get the same matrix back. So if we just flip everything over, we get exactly the same matrix. That can save us a lot of time if we're dealing with bigger problems. This one, it just saved us from maybe having to calculate one of the entries. If we have, say, a system where there's 3 variables, it would save us three calculations. If we have 4 variables, how many would that be? It would save us 6. And it actually ramps up even more. We're not going to get do some very big problems like that, but just note that we actually, if we do have a very big problem with lots of variables involved, we might actually need to do that. Or, well, not need, but it would save us a lot of work in that case. So, probably be taking advantage of that. That's a little bit of side note. We don't really need to be talking about that right now. But okay, now we want to take A transpose times B. So each of these rows is going to be multiplied by the column 5, 7, 1. So 4 times 5 plus 1 times 7 minus 3 times 1. That's going to give us a 24. And then same thing, 6 times 5 minus 5 times 7 plus 2 times 1. That's going to give us a negative 3. So we're looking for a solution to A transpose A times X, or X hat specifically, is equal to A transpose B. Well, let's just solve that system as an augmented matrix. We're looking for a solution to this. Now, we could have found the inverse of A transpose A, and if we're using a lot of different B's, that would probably be the best way to do it because we could use that same inverse multiple times. But if we're just dealing with one B, let's just do it this way. As an augmented matrix, we'll just save ourselves from having to do all that work and just essentially apply the matrix one time, or apply the inverse one time. Okay, we do some elimination. First thing I'm going to do is just divide everything by 13. All the entries on this side are actually multiples of 13. I'll get some fractions over here, but we kind of will end up with fractions anyways. So it'd be nice to be able to simplify this side. So this becomes 2, 1, 1, 5. Then over here we have negative, or not negative, the negative's on the 3. We have 24 thirteenths and a negative 3 thirteenths. Then we can go ahead, well, let's move this the second row to the first row to make use of that 1. And then we'll go ahead and change that 2 to 0 by subtracting 2 times the row 1, 5, negative 3 over 13. That's going to change this entry to a negative 9. And it's going to change this entry to a 30 over 13. So what do we have here? Well, keep in mind these represent equations. So we'll go ahead and just solve those equations now. We have a negative 9 times y is equal to 30 over 13. If we solve that, y is just going to be equal to negative 10 over 39. Went ahead and cancel out a 3 in that. Then we can use that solution to back substitute to find out what x is. We have the equation x plus 5y is equal to negative 3 over 13. If we plug in negative 10 over 39 and solve, we'll find that x is equal to 41 over 39. So our least squares solution is going to be, well, x is first, so the 41 over 39, and then the negative 10 over 39. This is not an exact solution. If we plug these into the system, we will not get exactly 5, 7, and 1, but it's as close as possible as we can get to a solution. And whether or not it really even gives us close to 5, 7, and 1 just tells us how close we could possibly even get. We can't get any closer than this one. Oops. Alright, let's look at a little bit bigger of a problem. So here we have 3 variables and 4 equations, still overdetermined. We're going to make our matrices. So here our A is going to have 4 rows and 3 columns. Our B is just going to be a single column, but with 4 entries. Of course, we take A transpose. Again, just for space, I'm going to put it over here. And then 7, 3, 1, 0. So note that we did have to include that Z as a 0 in this case. We'll go ahead and take A transpose times A. And I'm not going to go through all the details here. Hopefully you know how to multiply matrices at this point. But we're going to have a fun 3x3 matrix of 39, negative 10, 37. It's going to be symmetric so that we still have a negative 10 here and a 37 here. We'll then have a 51 and a 24. Again, from symmetry, this is also 24. And then we have a 59. Big numbers, but that's kind of typical. We'll go ahead and also find A transpose B. So again, each row times the same column. And we'll get a 24, 49, and 66. So a lot of computation, but it's relatively straightforward. We don't really have to think too much about that. Just do it. We'll go ahead and we'll use this as our coefficient matrix for our normal equations. This is our constant. So our normal equations just become the augmented matrix. And then 37, 24, 59. With the augmented part of 24, 49, and 66. Now, note, we could have just gone ahead and immediately wrote our A transpose A here and our A transpose B here and skipped having to write it out. Once you get more used to it, that's pretty straightforward to do. So we don't have to necessarily write down every little step every single time. But I just want you to have an idea of what things are what and where they're going. Okay, now we get to use Gaussian elimination. It's going to be quite a few steps here. This is a quite involved problem, and might suppress doing some of the actual calculations, but hopefully you can get the idea of what I'm trying to do. My first idea on this one is I'm just going to take this last row, this third row, and I'm going to subtract it from the first row. That's going to give me a nice 2 up in this case, in this part here. It's not 1, but it's a lot better than what we had before. Everything else I'm going to leave alone for the moment. I guess I'm going to have to move up here. Probably going to have to move to another page as well. Alright. One advantage of doing this is that first row is also now all divisible by 2. So we can actually go ahead and turn it into a 1. Oops. Wrong ones. Here. Actually need to divide by 2. So we'll get a negative 21. And then we'll go ahead and use that 1 to cancel out the negative 10 and 37. So we're adding this new first row plus times 10 to the second row, or to the old second row, and we're subtracting 37 times this first row from that last row. Give us some big numbers, but we can actually manage with it. So our new second row is going to be 0, negative 119, negative 86, and negative 161. Our new third row will be 0, 653, 466, and 843. Some big numbers in there. And now, rather than trying to divide one of these rows by one of these bigger numbers up here, I'm going to do a few little tricks. I'm going to take as many copies of 119 that go into 653, and I'm going to add that many times the second row to the third row. So 119 goes into 653 5 times with some remainder, and we're going to take 5 times the second row and add it to the third row. So that's going to leave our second row alone. But 5 times that row added to the third row will leave us with a 58 here, so a much smaller number, a 36 here, and a 38 here. So not too bad. And now starting with this on a new page, we'll go ahead and do a similar thing. How many times does 58 go into 119? Well, it goes twice. So I'm going to take 2 times this last row and add it to the second row. It's going to leave most of the stuff alone. In fact, it's going to leave the third line alone and the first line alone. But it's going to change the negative 119 to a negative 3. So I just added 2 times 58 to the negative 119, became a negative 3. And then we also get a negative 14 here, and a negative 55. Sorry, 85. Negative 85. At this point, things have gotten simple enough that we'll actually just go ahead and use what we have here. We'll go ahead and divide by negative 3. So we'll actually have it, well, the second row by negative 3 anyways. So that'll become a 1. We'll get some fractions here, but they're not nearly as bad as dividing by 119 or 653. So as we don't have too bad of fractions. And then we can use this new row, multiply by 58, and subtract it from the last row. Make that a 0 there. That will leave us with some fairly big fractions here. This will be a negative 704 over 3. And this will be a, actually this one's quite big, negative 4,816 over 3. So some big numbers there. But that kind of had to be true. Now we're in a position to actually finally solve our system. Basically, our last row is this number times z equals that number. In fact, since we can actually multiply that by 3 and not have to worry about that. So we have negative 704z is equal to negative 4816. And so z, and just simplifying it a little bit, is going to turn into 301 divided by 44. Then we use that in our second equation. We have y plus 14 over 3 times this z, which is 301 over 44. And that's going to equal 85 over 3. Taking 85 over 3, subtracting that, and simplifying. I'm going to assume that you guys know how to do that. But we'll get y is negative 79 over 22. Finally, we take our first equation up here. We have x minus 17 times y, which is actually a negative 79 over 22. We have a minus 11 times z, which is 301 over 44, is equal to a negative 21. Again, move everything over to the other side, do some simplification. We're going to get x equals to a negative 299 over 44. Our least squares solution in this case is negative 299 over 44, negative 79 over 22, and 301 over 44. That's the closest solution, or the closest vector, you could say, that to being a solution to the original system. So remember our original system up here. Won't give the exact numbers, but it'll be closer than any other thing possible. Now let's return to this line of best fit stuff that we talked about back at the beginning of the first video. This is kind of a more typical example of how this idea is used. Rather than starting with a system of equations already, we start with some data and we want to find some way to actually represent that data. So we have these 4 points. So we can actually plot those 4 points. So we have a point -2, 2, 5, 2, 9, 4, and 10, 5. And they may not look like they exactly fit a line. Well, in fact, they don't really fit a line. But maybe you can imagine that there's some sort of linear relationship between them. If we had more data, maybe that might be a little bit more clear. But let's see if we can find a line of best fit for that data. So how do we find a line of best fit? Well, it comes down to starting with the idea of the general formula for a line. We have y equals mx plus b. We don't know what m and b is, but we want these numbers here, these points, to kind of be able to fit into here. Maybe not exactly, but as close as we possibly can. So let's plug those points in. Remember here, our x values are our first ones, our y values are our second ones. So we have, I'm going to write them over here. So when y is 4, we want x to be 9. When y is 2, we want x to be, at least for this point, 5. In this case, we saw y equals 2, but this time we want x to be -2. So you can kind of see already that if one of these equations is true, the other one can't technically be true unless we just had a constant line where m equals 0. And that's not going to satisfy these other equations. So there's not going to be an actual solution, but there might be a least squares solution. Well, there is going to be a unique square solution. And then finally, when y equals 5, we're going to have x equal 10. This is now a system of equations, but our variables are m and b instead of x and y. I'm going to treat b as our first variable just because it has the smaller coefficients. That's pretty standard to do in these cases, and we'll be doing that in the second part to this problem. But what I have here is a matrix A, which we have the coefficients of b, the coefficients of m. We have our b, which is our constants. These are the y values that we had before. So we have 4, 2, 2, 5. And we're going to do the exact same situation as we did before. We take A transpose. A transpose has 4 1s, and then 9, 5, -2, 10. Went off the page a little bit, but it's okay. We're going to take A transpose A. This is going to be a 2 by 2. It's going to be symmetric. We're going to get 4 here because all we did there is add up a bunch of 1s. 4 1s specifically. Then our next one, we're going to have these 1s times that. So we actually add up our x's, and we get a 22. We'll get the same 22 over here. And then we end up multiplying this row by this column. So actually, we're summing the squares of the x's. And we're going to get 210. So again, we get a lot of squares when we do these actual matrix multiplications. That's kind of the root of why we call it the least squares method. Again, we take A transpose B. This is going to be a 2 by 1. And we're going to get 13 and 92. So we're trying to solve the augmented matrix. 4, 22, 13, 22, 210, 92. We'll introduce some fractions. Just going to divide this first row by 4. So we'll have 11 halves here and 13 fourths over here. We'll go ahead and use this new row and take 22 times it and subtract it from our second row. So 210 minus 22 times 11 over 2, that gives us an 89. And then 92 minus 22 times 13 over 4, that's going to give us a 41 over 2. Or in other words, remember this last equation is equivalent to m times 89 is equal to 41 over 2. Or in other words, m is 41 over 178. This first equation is b plus 11 over 2 times this value for m is equal to 13 over 4. And so b is then going to equal 353 over 178. So our m is 41 over 178. Our b is 353 over 178. We could put those together as our least squares solution. But remember what it's supposed to represent. It's representing this line of best fit. So y is equal to m, which is 41 over 178, times x, plus 353 over 178. And that's supposed to be the closest line to actually fitting our data. Let's see how close we got. Oops, there we go. This is our line that we just got, using the m and b that we just derived. It's fairly close to our data. It goes straight in the middle of them. Some points are on some side, some points are on the other side, but it's as close as we possibly can get to all of them. Now, maybe you'll say that, well, this point 5,2 is fairly far away from our line. Maybe this isn't really a linear situation. Maybe we're trying too hard to fit it into a line. Maybe instead it's a quadratic. We could try a quadratic. We'll start off kind of the same way. We'll start off with the general formula for a quadratic. And we'll use our same point. So remember, we had the point of 9, 4. So we plug those in here. We put 4 in here. We have to square our 9, so we get 81a plus 9b plus c. We plug in our point 5,2, so we have 2 for our y. When we plug in 5 here, we get a 25a, we get a 5b, and we still just have c. Then we'll try the point negative 2, 2. So 2 over here again. This one, negative 2 squared is 4. We have negative 2 times b. And then finally we have the point 10, 5. So 5 over here. And we have 100a plus 10b plus c. So here we have a system of equations with 3 variables, a, b, and c. We don't know what a, b, and c are, but we want to, and in fact, we can't necessarily solve explicitly for those 3 variables. There's actually not going to be a solution to the system of equations. But we can actually get a least squares solution. Just like the last time, I'm going to go ahead and order them kind of the opposite order. I'm going to put the c's first just because we like to put the smaller coefficients first. So what do we get here? We get a matrix A. We have four rows for our 4 equations, but we end up with 3 columns this time. And our matrix B, this is our constant matrix. It's actually the same b that we used before. If we take the transpose of A and multiply, I'm going to go, I'm not going to write out A transpose this time. Hopefully you can figure out how to find that yourself. But we are going to get a matrix, a symmetric matrix. In fact, part of this matrix is going to look very similar to what we had before. This 2 by 2 up here is exactly the same as what we had in the previous, our line of best fit solution. And we actually get two 10s in those two corners as well. But then we get some pretty big numbers for the other ones. So we have 1,846 in two places. And then we have 17,202. And our A transpose B, this is going to be a 3 by 1. So we have a 1,392 and 882. Now we got some big numbers in here. Maybe we don't want to do this one by hand. And when you get into some of these bigger problems, that becomes kind of one of those issues. But computers are really good at calculating with matrices. One program for doing that's pretty commonly used, and if you ever use matrices in your job after college, you'll probably end up using MATLAB. You may have actually even heard of that before. This stands for Matrix Laboratory. It's not Math Lab, by the way. It's not free, though. Some of the computers on Wichita State will actually allow you to use that. Not so easy to use that right now that we can't actually go to campus. What I actually use for free at home is another program called Scilab. It's a little bit different, but you can actually do a lot of the same kind of computations. One thing I'm going to note before I actually show you how that works is instead of this notation A transpose, they use the notation A with a prime. Technically, it's a different notation, but as long as we're not dealing with any complex numbers, it gives you the same result. So don't worry too much about that. So what do we have here? We're going to define our matrix A. A is going to be our matrix. Make sure I have this. I'm going to use the original matrix A. I'm not going to use the A transpose A. So this matrix had its first row was 1,981, and then I'm going to separate this first row from the next one by putting a semicolon. The next row is 1,525. The third row is 1, negative 4, or sorry, 1, 2, negative 2, 4. And our third row is 1, 10, 100. So it formats it really nice for us. It doesn't have the parentheses or brackets, but at least it can show it to us. B is our column, so just going to have to keep separating the rows by semicolons. So 4, 2, 2, 5. So remember our formula for how we actually solve that. We're going to take A transpose, transpose meaning A prime. I have to tell it to multiply that to A, and then I want the inverse of it. Do that by putting it into the function inv of that. So if we actually want to write out the inverse, it can actually compute that for us. We're going to take that result, and actually I'm just going to use their previous result by putting A and S for answer. I'm going to multiply it by A transpose, and then I'm also going to multiply it by B. And that gives us the result of three numbers. Remember, this is our three numbers representing C, B, and A. In other words, if we write that out, that's telling us that our quadratic, or you could say our quadratic of best fit, has A of 0.04 96735 x squared, then minus 0.1553299x, plus a c of 1.4964578. So technically these are all fractions, but the denominator I know already is 36,136. So we're just going to leave them as decimals. And a lot of these big complicated form or calculations with matrices, you'll just kind of do the same thing. If you're ever using MATLAB or Scilab, you're probably just going to work with decimals. So this is what our formula has given us for our quadratic at best fit. And if you didn't see the preview of that just a moment ago, that's what that quadratic actually looks like. So this looks a lot closer. It actually passes very close to some of those points. In fact, it almost looks like it passes directly through 10.5, though I think it's a little bit off. I mean, we could technically test it by plugging in the values of 10 and 5 and seeing if we actually do get an exact answer. But we probably shouldn't expect that. But it's really hard to say that this is far away from being an exact solution. It's really close to actually fitting our data. And so maybe that's what we'd want to use if we wanted to actually work with this data in some sort of model. Now, technically here, because we have 4 points, we could insist on going to the next step and looking at a cubic polynomial. We'd have 4 points, we get 4 equations, 4 variables for each of the coefficients of x cubed, x squared, x, and 1. And so we won't be dealing with an overdetermined system. In fact, it is possible to get a cubic that does actually hit all the points. And that cubic looks like that. This exactly passes through each one of those 4 points. Whether or not we want to say that really is a better model for that data may be kind of subjective. Maybe if we got more data, we'd find that they don't really fit this cubic. Maybe this cubic is a little too exact. We'd actually need more data to really see whether this is better or not. So more data always will give you a better idea of whether or not your models really do fit. But it's usually better to try not to use a higher degree than you have to. So the book has a pretty good example of that. So here they give you a set of data, and we can see the different points. We have a point here, we have actually, I think, 3 points there, we have 3 points there, and we have another point there. We have a total of 9 points, and you can see the 9 different entries here. It seems pretty obvious that they are very close to fitting a line. And they drew the line of best fit in there, and without zooming in, it's really hard to tell that those points aren't on the line. But if we think that we have, well, 9 points, so we need an 8-degree polynomial to really hit every single one exactly, we can end up with an 8-degree polynomial that actually does pass through every point, but in some way doesn't really seem to fit the data correctly. It feels like this is thrown off quite a bit. And the problem is that this 8-degree polynomial it's too sensitive to all the little tiny errors. Any tiny little error in these points will throw it off quite a bit. And so it's just maybe a little too exact. It's actually better in this case to use a smaller degree polynomial. In fact, it'd be easier to find that anyways, just because the calculations for finding a least squares line involve smaller matrices than one for this 8-degree polynomial, because that would involve a 9 by 9 matrix instead of when you take A transpose times A instead of the 2 by 2 matrix that we're always going to get when we do a least squares line. So just kind of be warned. Maybe not trying too hard to get to the highest degree possibility is actually better, which is actually kind of nice that we don't have to go to that extreme unless for some reason our line doesn't really fit the data very well. If we can get really close like we have here, that line is great. If our points were way more scattered, if our points were all over the place, maybe a line wouldn't fit that very well. We have to play it by ear. Maybe some other curve would fit better then. We'd have to try that out. The book has a few other examples, like it has one where it wants to fit points to a circle instead of a line. Take a look at some of those, see how you like those. But I'm not really going to go any further than looking at quadratic, just because the calculations can get a little tedious, but they're always pretty much the same thing. So hopefully at least you got an idea of how this stuff works, how we can proceed on these kind of problems. It's not very hard to actually know how to do them. It's just going to be a little tedious to actually perform the computations. If you have any questions, you can always see me in my office hours, and I'll see you again in the next section, in section 5.4. 5.4 is not going to be as calculational. We'll go back to some of the theory. So I'll see you then.